Please each team check your connection. So as a reminder that there's no video tagging, photo, and also no Wi-Fi during the time. And for the reporter and for the speaker, please speak loud so the jury can hear you clearly. And also when you make a discussion on the blackboard, please also try to move around a little bit so that the jury can see what you write down on the blackboard. So if connection okay, recording okay, reviewer okay, phone okay, good. So let's start the fight. So opponent, please challenge the partner.
We would like to challenge problem number 4, shooting over gas.
That would be partner number number 4. Shooting rubber band. Okay, well, challenge your set. You have 5 minutes to prepare. You need starting time. Please, representing, write your name on the blackboard. You may take your floor.
Recent fellow competitors, I am the reporter from Team Overballs, and I'm going to report problem number 4, shooting rubber band. So, a rubber band may fly a long distance if it's non-uniformly stretched when shot. Given it a spin, I need to optimize the distance that a rubber band with its spin can reach. So the main focus is the way of non-uniformly stretching, and also the distance and the path offsets during the shooting, and the distance with or without direction, like if I consider the path offset or not, and if I shoot the rubber band horizontally or vertically. So for the observation part, I will show the video for the spinning, shooting, and also comparing the shooting. And also for the theory part, I will consider the energy transformation during the shooting, and I'll talk about the Magnus effect and the lift force that caused by it, and the horizontally and the vertically spinning, the difference between them. So for the observation part, we can see that when a rubber band is stretched with one side more than the other, it flies straight to the other side. And in this video, we can see that the rubber band is spinning while it's shot. So this is the video of a uniformly stretched rubber band. So we can see that the red square is where the rubber band landed, and this is where it's non-uniformly stretched, and we can see that the distance is further and the path offset is smaller. So for the energy transformation, we know that when the rubber band is when the rubber band is pulled, it will have an energy stored in the elastic material, which is the elastic potential energy, and when it is released, it will be transferred into the kinetic energy and also the rotational energy. Yeah. So we can see that in this picture, the A side has a longer stretch and the B side has a smaller stretch. So we can see that the A side will contain a larger potential energy. So when they are released, the A side will cause a larger velocity and also a rotational velocity. So that is why the rubber band will start rotating. So this is how the rotational of the rubber band will affect the air and also its movement. So we can see that due to the Bernoulli's principle, when the rubber band is rotating, they will have a higher flow rate on the side that is rotating the same side with the rubber band, and the velocity of the flow rate will become larger, so there will be lower pressure. And so we can see that between these two, they will cause a lift force. So if the original direction is straight, the influence direction will become higher. So this is the difference between the horizontal and the vertically spinning. So as I've mentioned before, when the rubber band is rotating vertically, the influence direction will make the rubber band fly higher. And when the spinning axis, when the rubber band rotates horizontally, the influence direction will cause a larger offset on the path, and also it will be horizontally stabilized because it rotates in a horizontal way. So this is my experiment setup. So I set up different initial points to set the initial length of both sides of the rubber band different, and then I pull it to the 20.5 cm, so we can see that A side is stretched more than the B side. And so I consider this I consider the both sides stretched is the 20.5 cm because the circumference of the rod tip is really small than the circumference of the rubber band, so I just ignore it. And so this is the shooting direction, and there will be an end line, and I will calculate the path offset and also the distance. And this is my device for shooting. So the 20.5 centimeters is where the rubber band is placed. So these are the values that I want to measure. First of all is the flying distance, like the distance without direction. How far does the rubber band actually go? And I will measure the D2 to calculate the path offset. So later on I will talk about like delta S, and I define delta S as the difference between the initial length of D1 side and D2 side. And also, as I mentioned, that when the rubber band is vertically spinning, it will cause a lift force. So I want to measure the trace of line to get the height of the displacement, to get the height displacement. So before that, I need to calculate the K value of a rubber band. So in my experiment, the rubber band is extended in this range. So we can see that in this range, it is a linear line, and I get the K value for 0.022, which the unit is like that. So I see the rubber band as two springs related together. So one of them, the value will be divided by 2. And so we can know that one string of the rubber band, the K value is 0.011. So when I separate the rubber band into D1 and D2, I considered it like I am cutting off these two parts because I'm separating them 2 and 2, that's both of them. So the K1 and K2 ratio will be like this. So the tension ratio will be like this equation right here. So the delta X1 is the 20.5 subtracted by the original thing. And these are my variables in the experiment. First of all is the unequal stretching, where I change the initial length on both sides. And second is the placement of the rubber band, like I shoot it horizontally or vertically. So these are the things that I want to measure. First of all is the flying distance and also the straight distance to calculate the path offset. And I will measure the height difference in the vertically spinning one. And so experiment 1 is when I shoot the rubber band horizontally. And we can see that when the delta S is 0, we can see that there is a larger difference between the 5 times of experiments. And when the tension ratio becomes smaller, we can see that there is a peak where the delta S is 3 centimeters in this experiment. And we can see that when the delta S becomes larger, it starts to decay. And this is the straight distance, and we can see that there is also a peak when the delta S is 3 centimeters. And if we calculate the D1 and D2, we can get the path offset, which the angle will be like this. So we can see that the path offset of the delta, when the delta S is 0, there is a really huge difference between each time of experiment. And I think that is because when you didn't, you extend the rubber band uniformly, there is no rotational velocity to stabilize its flying. So it will be easier to be controlled by the turbulence or the wind in the environment. And experiment 2 is for the vertically shooting. So these are the data, and we can see that the peak of the vertically shooting is at when the delta S is 4 centimeters. And the height displacement, there is also a peak at when the delta S is 4 centimeters. So comparing these two, we can see that the green dots are the one vertically shooting, and the red dots are the one horizontally shooting. So we can see that all of the ones that are shooted vertically were further than the ones that are shooting horizontally. And we assume that it is because that the lift force that I've mentioned before helped the rubber band to can fly to a further distance. And so in conclusion, we can know that for the first part, for the same stretch length, the shooting vertically flies further than shooting horizontally, like this graph shows. And so when in experiment 1, we can see that when the rubber band is shot horizontally, when the stretch difference is 3 centimeters, the rubber band will reach the furthest distance at the smallest offset angle. And when the rubber band is shooted vertically, the stretch difference will become, when it's 4 centimeters, the rubber band will reach the furthest distance and also the largest lift height. And so to shoot the furthest, we can choose to shoot the rubber band vertically and with a stretch difference in 4 centimeters in this experiment. And the furthest experiment that I've done is about 537 centimeters. And for the discussion part, I want to talk about, because I've mentioned in the theory part of the energy transformation, but I didn't calculate the ratio between how the potential energy transforms into the kinetic energy and rotational energy. So I think in my further experiments, I can done is first I have to calculate the initial stored energy, and then I have to track the trace of the rubber band to calculate the velocity to get the kinetic energy. And so I had to calculate also the rotational velocity to calculate the rotational energy. And I can get the ratio and also the dissipation between the energy transformation. And second part, I think I should consider more about the influence of the turbulence and the wind. I think in my further experiment, I can involve a fan into the experiment, like when there are winds affecting the flying or not. And I can try to blow in different directions to investigate the distance and the height lift and also the path offset when there are different kinds of wind or turbulence affecting this phenomenon. And so I can optimize what is its character in this experiment and get the furthest flying distance considering the turbulence and the wind. So this is the end of my report.
Okay. Any question?
Thank you for your presentation. Can you go back to slide 7? In the video, in the horizontal video, the rubber band is actually contacted with the ground. Did you consider the force that the rubber band will experience when it contacts with the ground?
It did.
Oh,
this one?
Yeah.
So the distance that I measured is when it first touches the ground.
Did you consider the energy loss between the ground and the rubber band?
No, because I measured it.
Can you go to slide 8? Did you consider the factor of dynamic buckling and the Euler's theory structure?
No.
Okay. Can you go to slide 10? You used the Bernoulli's principle to calculate the Magnus effect. Did you? But how do you know the flow will be magnetized? The flow will not be turbulent, or surrounding the rubber band.
I'm focusing on the flow rate here, the difference of the flow rate, so I can know the influence direction will be in which
But doesn't
direction.
the Bernoulli's principle is supposed to have the air to be flying? Okay, next question.
This is in the ideal.
Can you go to slide
condition.
11? Did you consider the horizontal torque on the horizontal flowing rubber band?
No?
No. Can you go to slide 12? For the initial potential energy equation, did you consider? We noticed that you changed the K value according to different stretching points, but did you also consider the difference in displacement? Because that is a major part of the equation.
Yes. Right.
Okay. Slide.
Here.
Slide 14. Could you clarify why you think there's an offset for the slides?
Because in my experiment, I find out that there.
Okay, sorry, time is up. So, Conan, you have 5 minutes. So you have 3 minutes. Opponent, you may take it for 3 minutes before 4 minutes.
Hi, I'm Chaewon Bae from Rubber Band, and we're Team All-Nighters. And the problem statement is that a rubber band may fly a longer distance if a non-uniformly stretched rubber band is shot and giving it spin. And the problem states that we should optimize the distance that a rubber band with spin can reach. So our ideal structure of investigation is that first we observe what will happen in a video of a phenomena demonstration, comparing the uniform rubber band and the non-uniform rubber band. And then we go through an energy analysis of the conversion of energy between potential energy and kinetic energy. And then we analyze the additional forces of drag, flow of air, and lift force. And then we conclude our experiment. So our structure of solving a problem is that first we observe how the rubber band gun the reporter provided will change, and then we will talk about the theory, which is the energy combining elastic energy, gravitational energy, and that leads to translational and kinetic energy, and the magnetic effect and lift force and the spin axis. And the experiment, we compared launch at various offsets and vertical and horizontals. So the pros and cons of the report was that the pros was they replicated the phenomenon very well, and they had accurate graphics, and they also had error bars in their report. And they also found an optimal offset. However, these are some cons we found in the experiment. They did not consider the various types of rubber band, and, because the elasticity or the rigidity will change the trajectory of the rubber band. And the setup causes an additional loss of kinetic energy because of the contact of the rubber band and the gun. And there was no clear free body diagram to describe what was happening in the rubber band. And the theoretical model is not properly justified. Also, the graph was not explained very clearly of how the rubber band is going through the forces. And the reporter also did not justify the reasons for laminar flow. So in our points of discussion, we will discuss whether the rubber band experiences laminar flow or turbulent flow, and the various types and the impacts the various rubber bands has on the experiment, and also the reasons for offset. And we also want to discuss about the drag forces and what additional forces that will impact the rubber band force. Can we move on to the discussion?
Okay, move on to the discussion.
So you mentioned that there was laminar flow in the rubber bands, but how do you know for sure that the rubber band experiences laminar flow?
I didn't mention. Can you explain what is that?
Oh, laminar flow is something that should be essential when it comes to applying the Bernoulli's equation, because Bernoulli's equation operates on the fact that when the fluid is flowing in a surface or like in a fluid, the fluid should flow laminarly. But if you do not know for sure that the air surrounding the rubber band is laminar, then how can you apply the Bernoulli's equation, Bernoulli's principle? Laminar and turbulent flow.
Okay, so in my theory, that is for an ideal condition, and also that in my experiment, I done the experiment in like inside.
Inside.
So
What do you mean by inside?
like there's no wind or some other factors, so I think like I can consider it like the turbulence of the wind will become smaller. Indoors.
Take for example an airplane. An airplane flows because of Bernoulli's equation because of the pressure difference. However, for the case of rubber bands, especially when the rubber band is rotating like this, like not in a particular trajectory, it is not very stable. It's like it goes like very flimsy, and that will significantly cause the air surrounding the rubber band to be very turbulent. What are your thoughts on this?
I think that so for the ideal situation, when the rubber band is shooting, the rotating actually makes it more stabilized.
How
Like take frisbee for example. Like when you fly it, it actually stabilizes. Like it doesn't move a lot because of like it rotates.
But don't you know that? But that doesn't apply when it's going horizontally. But
Yeah. So when horizontally, I said that the influence will be higher and not stable.
okay. Our suggestion is that you use the Reynolds number to calculate whether the air surrounding the rubber band is laminar or not. It's a equation that you can use to plug in the numbers to decide whether it's laminar or turbulent. So that's a suggestion that you can use for your further experiments. And also, how do you consider the air resistance and drag force into consideration in your experiment? Because when the rubber band rotates around its trajectory, it definitely experiences some sort of air resistance. However, we realized the reporter did not significantly mention that part in the report. So did that?
Okay, so I think in my experiment, I am comparing like when I'm all horizontally shooting and vertically shooting. So I think in the way that I am horizontally shooting, they all undergo the air resistance.
Oh, are you saying that the air resistance for both rubber bands it experiences the force same?
Yeah,
the air resistance is the same for all rubber bands?
Yeah, and it also like motivates the horizontal airflow.
What do you mean by motivating the horizontal airflow?
When the rubber band is flying and rotating,
Yeah.
like what I draw here.
Yeah. So you're saying when it's flowing faster, it's going to become more stable?
Yes.
But how do you know that it's going to be horizontally stable?
Like in this model.
How do you know that like when it's like that? When it's rotating faster, you know that for sure. It's
May I?
Oh yeah, sure.
So the rubber band is flying like this.
Yes.
It's rotating.
Yeah.
So the airflow, the flow rate will be faster right here, right here. So in the direction here, it will deflect it to a further equal. But however, that is all in a horizontally. Like these are all in one flat.
Then how did you calculate the velocity of the rubber band? Because because we thought there are various methods of calculating the velocity of the rubber band, whether it should be the very last part of the rubber band or the very front part of the rubber band. How did you calculate the velocity of the rubber band?
I have mentioned in my discussion that I have been doing this, but however, in my experiment, I have observed that when you shoot a rubber band, when you release it, the backside, like this is the direction, the backside actually chase onto the front side initially, and then it will gradually turn back to its shape.
Yes.
And fly further because of the energy transfer into the velocity. But initially, there will be different velocities in the front and the back. But however, during the flighting, they will become stabilized. And what I have measured is like the whole distance.
Oh, so you're saying you did not consider the difference these two both in oh, okay. So a suggestion you can adopt to track the velocity of the rubber band is calculating the front part of the rubber band and the last part of the rubber band, and calculating the velocity of the center of mass so that it makes the velocity of the rubber band more accurate. So that could be a discussion. That could be a suggestion. Because even when it's rotating, there's even when the rubber band is rotating, it wouldn't always go through a shape like that. It wouldn't always be a circular rotating shape, or it could have some changes when it comes to flying. So if you want to calculate the precise velocity possible, then it is better to calculate the center of mass between these and these 2 points, so that when it flows, like you know for sure where you can have a point that the velocity is actually moving to make the flow better.
So like if I change the initial distance, so this one is tighter and this one is not tighter, what do you think will affect?
If this one is tighter and this one is lighter. In my opinion, we think it's going to create more rotation. And also, for the part where you mentioned horizontal stability, do you think the faster it rotates, the more horizontally stable it is?
I think there will be a best ratio because, for example, when let's assume that we took a really, really small, and it will actually, like I told you, it will only rotate and not go too forward. And like if you set it here and here, it will just fly and not rotate. So
how do you know that if you rotate it simply, it's not going to rotate if it's stretched uniformly?
So in my ideal model, the energy here and here will be the same, and it will transfer to like ideally the same velocity and the rotation velocity. So when the both sides of the rotation velocity is the same, I can assume it.
Are you saying the velocity here and here is going to be the same?
Like when
It's going to cancel out.
No, not cancel out, but the two sides, because the rotation is because like the V here is larger and the V here is smaller, and the rotational velocity here is larger, so it rotates more. Right?
Oh, our question.
So when both sides is the same, I will say that it flies further, but without too many rotation. But in this case,
So you're saying it's not going to rotate at all when it's uniformly stretched?
Yeah, in ideal condition.
In ideal condition?
Yeah.
What do you mean by ideal condition?
Like in my model.
Just no air resistance.
Yeah.
But moving on to the next topic, so you mentioned that the faster it rotates, it's not going to affect the faster it rotates does not impact how much the stability it has, because when it rotates faster, doesn't it have angular momentum and torque that gives it more lift force, and the time of flight of the rubber band it becomes faster, it becomes longer, so that will lead to a longer distance.
Yeah. So in this experiment, I mentioned that there is a peak when is 3 centimeters in the horizontal.
What is
This is like this is D1, this is D2, and the initial length difference.
initial length difference? Okay.
Okay, so as I mentioned, when this is extremely small, it will rotate more, and when it's the same, it will fly further. So I can believe that in between these two, there will be a ratio when the delta S is, and if somehow there is a value.
How do you know that there's a rotation? How do you know that there's an ideal ratio?
Like I want to find it out in my experience.
Oh, okay.
Because by these two things, I can know that there will be a middle range of flying and also stabilizing.
Oh,
So, and in my experiment, I found out that it is obviously reaches.
can you go to graph where you compared the horizontal velocity and the vertical velocity? Over here, we observe a very big difference between the flying distance. What are your thoughts on the very big distance? Very big difference between these and like these two results. What are your just general thoughts?
I think that is where the best ratio happens. So it can be like the most stabilized, and also the velocity and the angular velocity can bring it to a furthest and most stabilized place. So that is where there can be a big gap.
So you're seeing the difference in the stretched length between the two parts. It's going to occur at 4.
This is horizontally. The red dots.
No, but then for this green ones, the peak is at 4.
Yeah.
So and that's 550. So
Alright.
doesn't that mean?
Time's up.
Thank you.
Okay, so opponent, you have 1 minute to summarize the discussion.
In our discussion, we first talked about the laminar flow and the importance it has on discussing the Bernoulli's principle, and also we discussed how horizontally stable the rubber band will experience when it goes through a trajectory, considering the angular momentum and the torque. And we also considered how the shape of the rubber band will change and how that contributes to the drag force change in the rubber bands. And and we also talked about the data analysis of the height displacement between the different lengths. So the reporter talked about how there is an optimal ratio in the rubber band, and that will occur at when the distance difference between the two parts of the rubber band is at 3 and 4. And as an opponent, I pointed out that the laminar flow is very important when applying the Bernoulli's principle into consideration, and also that the reporter should consider drag force in the.
Okay. Question from the reviewer.
So first of all, I have a question for the reporter about your experimental setup. So I want to know, how do you calculate your shooting distance?
I measured from the starting point to the end.
To the endpoint, you mean that the place it fell off
Yeah.
it drops on the first.
Yes.
But how do you do that?
There is ink on the rubber band, and it will like stamp onto the floor.
But however, if the rubber band is spinning horizontally, the drop the rubber band's drop point will not be visible. It's shooting.
There's a range of ink, and I calculate like the middle point of the rubber.
So the point, I have a question. How do you think of her experimental setup? Do you think there are areas for it?
We definitely think there are areas for improvement, especially when calculating the velocity of the rubber band, because the opponent did not consider the center of mass of the rubber band. And the experimental setup, we think the reporter should have tried out with various rubber bands with different elasticity and lengths.
So my second question for you is, as you're stretching the rubber band, the area of the rubber band will change, right? As you're stretching, the area of the rubber band will change. So do you think that applying the Hooke's law is good for calculating the K value?
Yes, because I think I have changed the K value when I changed the delta S.
So opponent, what do you think?
Can you state the question?
I asked her as she is stretching the rubber band, the area of the rubber band will change. So is it suitable for her to use the Hooke's law to calculate the K value?
Because her experimental setup, she used a rubber band gun in order to stretch it and shoot the rubber band out. We think it's a reasonable solution to use. However, the experiment would be improved if she instead calculated the potential energy and plotted it against the graphs.
In this range. Both sides
moving on
is
to the next question. So My final question is, do you consider other energy created during your flight process? So during your flying, the rubber band is vibrating, so there must be some rotating energy and vibration.
I consider them as the energy loss, like the not stable.
As for the point
We think in the initial part, the reporter's theory is reasonable, but the reporter did not consider the after parts, like terminal parts. Like when it actually flies, there's a lot of like sources of losses of energy, but the reporter did not consider that.
Okay. So, reviewer, you have 2 minutes to prepare your report. Okay, so reviewer may take the floor.
Okay, so I'm the reviewer from Team Faculty, and today I'll be talking about shooting over the. So first of all, as for the reporter, she has highlighted some main points in the problem statement, and she also has a clear demonstration, and along with some clear diagrams with adequate explanation during her presentation, and some sufficient data and error bars are also included. But however, there are some points of concern where she didn't discuss a lot of different parameters that will affect this phenomenon, and she also didn't consider some energy loss, such as wave energy, not mentioned during the presentation. And she also lacks the explanation in measuring how she measured the shooting distance in her experiment. As for the opponent, I think that she understood the reporter's presentation pretty well to a level, and she also mentioned some flaws in it during her presentation, including the misuse of the Bernoulli's principle. And the opponent also mentioned some critical points. But however, I think the opponent has too focused on the theory discussion and lacks discussing on her experimental setup, which we think that there is a problem. So, as for the discussion, the opponent first asked the reporter that whether Bernoulli's principle is suitable for the experiment because the flow is in laminar. The reporter replied that it was viewed as an ideal situation, so the flow should be viewed as laminar. So as for the second question, the opponent also asked that how was the velocity calculated when the rubber band is spinning? And the reporter answered that she didn't calculate it. And the opponent also asked that it also stated that it should be calculated using the center of the mass of the rubber band. Then the opponent continuously asked that if the rotational speed increases during the flight, will the rubber band be more stable? And the reporter answered that there should be an optimal speed where it is the most stable for a rubber band to be used. And the opponent also asked that why was there a jump in the reporter's graph, height displacement during the when she's talking about the height displacement, and the reporter answered that the jump symbolizes the optimal ratio in the rubber band when the distance is around 3 and 4 centimeters. So here are my questions for the reporter. So I first asked her, how did you measure the shooting distance? And the reporter replied that we used ink to mark the rubber band. My second question is, can Hooke's law be used to calculate the elastic force? Will the cross-sectional area be different? The reporter answered that she calculated the K value and it matches with our data, so the Hooke's law should be suitable. And the opponent agrees with the reporter. But however, we think that the cross-sectional area will change as the rubber band stretches. So we think that is a better way to use the Young's module. My last question for the reporter is, did she consider the wave energy and rotational energy during the flight? The reporter answered that it was viewed as energy loss, and the opponent also thinks that it needs to be considered. But from our point of view, we think that rotational energy and vibration energy should not be considered as energy loss. That's the end of my presentation.
Okay, thank you. And now the reporter for your conclusion remarks.
Thanks for the opinion and your review. So here are my concluding remarks for my report. First of all, the Magnus effect is a parameter that influences the speed of the airflow, which I've mentioned it as the Bernoulli's law. And to answer the opponent's question, we think the airflow is laminar because we considered it in an ideal condition. And third, we didn't consider the unstable. We didn't consider it unstable. And so fourth, the air resistance will not influence so much in my experiment because they all undergo a air resistance. And we think that the rotation is mainly caused by the non-uniformly stretching, so it leads to a different angular velocity. So to answer our opponent's question. And sixth, we use the middle point of the ink that we draw to determine the distance. And seven, the best distance would be like in two extreme conditions. One is equally stretched, and the other one is you only stretch one side, which it will only rotate a lot. And so the distance, the best distance would be between these two. And in my experiment, I found out that the delta S is 3 centimeters and 4 centimeters for horizontally and vertically shooting. And we think the spinning can neglect the partial of the environmental turbulence more because it can create an airflow around the rubber band, which will lower the turbulence. And the vibrating energy is counted as an energy loss in our experiment. And we think that the rubber band cannot be seen as a mass point, so using the center of mass might need more consideration. And last, we think that the stableness isn't only considering the rotating speed, so there should be a best speed. Thank you.
Okay. Now this question from the jury.
So, first question, if you want to get the optimal distance, what do you do? I mean, the structure you want to what kind of condition you get?
Like the
You want to calculate the optimal flight distance.
I will stretch it in like the peak I found where it will fly the furthest, and I will choose to fly vertically because I found out that
So you want the rotating vertical. About opponent, you agree?
About the ratio?
If you want to get the longest distance,
We personally agree with the fact that there might be an optimal ratio, but the general trend is that the more imbalanced the tension it has between the two parts, there will be more rotation happening, and that would cause more horizontal stability. So that would like make the optimal the distance it flies a bit longer.
What do you do?
I think that we should calculate it with as the rubber band is being shot first, because she mentioned that there will be no lift force according to the Bernoulli's also. To get the optimal shooting distance, the longest shooting distance, we should see it as a vertical on the stage to calculate.
I got a question for the reporter. I saw the video. You shoot the rubber band on the floor, okay? So the distance you measure is until the rubber band stops. Okay? So my question for you is that when you do the vertical pipe, if you stretch on the upper part or lower part, will that make any difference?
So the gun, the height between the gun and the floor is 13 millimeters, and I need both the gun to shoot horizontally and vertically.
That's right, but for vertical pipe,
Yes.
if you stretch on the upper part or the lower part, will that
Stretching on the upper part and lower part will change the rotating direction, and that will change like the force will be.
which one will make the shooting distance longer?
When the rotating direction is lifts the force like this. So if the rubber band is shooting here, it needs to be counterclockwise.
I have a question. Well, maybe Owen. Owen emphasized that this Bernoulli principle applied to the laminar flow. So you do that agree with the reporter's use of this theory. So in your point, from your point of view, if you, how do you, what kind of principle or rule you apply to this case?
We believe that the experimental setup was partially laminar, but there are definitely some turbulent air forces in the rubber band. So we believe we can adjust the setup to make sure the airflow is more laminar, or we can use other principles to take the turbulence into consideration.
That will contribute to what consequence in this experiment? For example, make it fly shorter or make it...
Oh, so if it goes through a laminar flow, and if we use the Reynolds number to actually prove that it has a laminar flow, it would just like yield the same results as what the reporter reported. But if it is actually a turbulent flow, then that would significantly, we have to enhance the reporter's results of the distances, because because in her setup, it was an ideal situation. So that means if the ideal situation was actually turbulent, then the actual distance will be much longer. So she would have to adjust all her data points to take that into consideration. So in the graph, the data points will be placed a bit higher in terms of like distance and other factors.
I have one more question for the reviewer. You mentioned about this other type of energy, for example, vibration, and you said it's not a dissipated energy. It's just
non-energy.
Yeah. So what does that energy help with this flight?
I think it mostly affects not the length of, it's the motion the rubber band is during the flight. It affects whether the direction of the rubber band or like the angle it's being turned. So we think that by calculating the vibration energy or rotational energy, we can discuss about how the motion of the rubber band will change, but not mainly about the distance.
Okay, more question. Because if you consider an ideal case, if this is not a rubber band, this is a bullet, which the RE, do you think the spinning bullet can shoot farther, or not spinning body can shoot farther. For example, reporter can answer the question first. Bullet without any internal degree of freedom, which is a reach far.
I think a rotating bullet is similar to like the vertically shooting that I mentioned. So I think that it can fly farther.
So is this relevant to the magnitude effect?
Well, the bullet is like the velocity of the bullet is really large, so I think the velocity affects more. But there is a speed, so there is like in my experiment it is closer to the vertical shooting, so I think it will still be farther because of both spinning and things.
We also agree with the fact that since a bullet has a much faster velocity than a rubber band has, that faster velocity will make it possible to neglect all the other factors that inhibit the rubber band's flight. So we could assume that for the case of a really fast object like a bullet, we could take that.
So do you think magnetic effect matter?
We don't think we think it matters to some extent for the case of bullets.
So I think that as we change the rubber band to a bullet, the main factor will be the rotation of the bullet is more stable than the rubber band. So I think that the more stable it is, the longer the effect.
I think it can like lower the air resistance, so it can fly the velocity.
Okay. All right. So if no further question, let's take the score. Okay, so let's show the score. First, the score for reporter. Four, 5, 5, 8, 7. So the score for opponent. 7, 6, 5, 7, 5. And the score for reviewer. 5, 5, 5, 7, 6. So maybe the shortcoming come out from about the reporter got the highest score.
Yeah, I think compared to last two find and so on, I think the reporter give a quite clear, much better previous two colors. So I give a better, that's too fine.
So, any more comments? No? Okay, so no more further comment. Let's conclude the fight this morning. Thanks everyone.